nicely for substitution. Really not. If I tried to get this to be an x equals or a y equals, it would be very unpleasant. There would be fractions everywhere. Ew. But this is actually set up quite lovely for us for our elimination that we talked about yesterday. Shock, what? Oh my gosh. Relevance to what we just did? Who's she? Don't know her. So, when we're given two equations like this, we look at our coefficients, the numbers in front of the letters, to see if I have the same number with opposite sign on one letter. So in this case, we've got our minus 4x with the 3y equals negative 3, and 4x minus 5y equals 5. Well, I see here on my x's, got my minus 4x and my plus 4x. Same number, opposite signs, score. We don't have to do any multiplying to get this to eliminate out. We can just go. So when we start this process for our elimination, what am I going to do with these two equations? Cancel out the 4. And we're going to do that by adding them, old school columns. So my minus 4x plus 4x is going to give me how many x's? 0. There's none x's. I like to write it down because it likes to see that we actually did it. You don't have to, but you can. What about when I take my 3y plus negative 5y? Negative 2y. We're going to have our minus 2y. And then we have our minus 3 plus 5. So, yeah, positive 2. So when we add these together, we get 0 x's minus 2y equals 2. Well, we don't typically write something when it's times by 0. So I can just like drop this piece off. The whole point of doing elimination is that somebody should go away on this step. So in this case, it was my x's that went away, and we got that minus 2y equals 2. So what's our y going to equal? How do I get to that solution? How do I get to a y equals? Divide by negative 2. So what does our y equal? Negative 1. 2 divided by negative 2 gives us a negative 1. Excellent job. We're done, right? That's my whole answer? Almost halfway. Because I have my y, I need my x, and we have to write them as I point. Can't just give me y equals and x equals. I need both as a point. So we can figure out what x is. How? Substitute it in. To what? Either of them. I can use the top one, I can use the second one. Genuinely, it does not matter which of these we use. We should get the exact same answer. I heard this someone say the top one first, so I'm going to go with that. So we're going to take our minus 4x plus 3y, what's this guy, equals minus 3. Well, we know our y is going to be minus 1. So we're substituting that in place of the y. And now we're going to try and solve this to figure out what x is. We've got our minus 4x. When we do this multiplication, 3 times minus 1, this becomes minus 3 equals negative 3. Then what should we do? Add 3. We've got our minus 4x equals 0. So what's our x going to equal? How do we get there? 0. Because I would divide by -4. I can split 0 into 4 pieces. I think the negative. I have no cookies to split among my 4 friends. I can have no cookies. It's 0. 0 does divide by 4. We cannot divide by 0, but 0 can be divided by anything. It's just 0. So my x is 0, my y is -1. That means my answer is the point 0 minus 1. This guy is my answer. We have to write it as an ordered pair. It's important. Questions? Okie dokie artichoke. We're going to work on something that's going to feel very, very different. Familiar, but different. Real quick. We are going to go on page 16 in your notes packet. There it goes. We've done these before, but it's been at least a couple weeks. So we're going to remember how to do them, because the next thing we're going to have to do is systems when they don't have the equal signs. Gross. So we're going to look at inequalities, and we need to remember how we graph those. Yes, dear?
When you just saw them down, why was it +3 +3?
Because we had -3 right here, and I'm trying to get x by itself. So I get rid of this -3 by adding 3 here, because I want this to be a 0. And so I added 3 over here. It doesn't matter that this one was
I thought usually you would have to do like the same sign, and then like it would cancel out, and then you bring the sign to the other side.
only if we are like multiplying.
Okay.
We would do the same sign. So adding and subtracting, it's going to be the opposite one. Good question. Good question, Elliot. All right. So we're going to remember how to graph these inequalities. We've done them before. It's been a minute, but like it's a thing. So how do we graph something like this?
You put on -5 all the way out to -4.
Yeah, we're going to start at -4 because this is in our slope-intercept form. That's our mx plus b kind of vibe. So we know we're going to start at that -4. That's our y-intercept. So I can put that point on there. Our y-intercept at -4, that's down here. This guy. How do I find my next point?
You go down 3 and
Close.
up 2 over 3.
Up 2 over 3. This is our rise over run. Up and to the right is kind of our default state. If we don't have any negatives, that's the way we go. So we're going to go up 2, right 3. Up 2, right 3. The more points we have, the easier it is to connect them up. Am I connecting these up with a regular solid line?
No, that line.
Why not?
Because it don't got a line under it.
Because I don't got a line underneath it. This guy means I need to draw a dotted line. Dotted, dash, however you word it. I don't really care. But it needs to be a not regular solid line. Should be something that-ish. You could do dotted, you could do dashed, however you want to think about it. But because we don't have that equals to, I need to do a dotted line. Am I done? No. What do we need to do? Shade. We gotta do some coloring. Yay, coloring. Where do I color though? Why?
One said white again.
And that this only works when y is on the left. If y is greater, then yes, you can go up. Y less than would be down. If we don't have y on the left, we have to pick a point and test it. So if y is on the left and we have it in like slope-intercept form, you can do that. We always kind of did it with a test point before. So I'm going to do the test point just because we hadn't done that, but that works, but only in very specific circumstances for those of you that knew that bit. So I'm going to go ahead and do a test point. I'm going to test 0, 0, just because the test point will work every single time. The greater than means up, less than means below, only works if y is on the left and x is on the right. So it's very specific. So I'm just going to test a point. If we get something true, we color where the point is. If we get something false, we color where the point is not. We want to know if 0 times my 2/3 times 0 is in fact greater than. So 2/3 times 0 is just 0. So this is 0 in fact greater than 0 minus 4? So is 0 greater than -4?
Yeah.
Yup. So if you have slope-intercept forms, we can use the above-belows, but that's very, very specific. Test point works no matter what form we're in. So since 0, 0's testing is true, that means I want to shade where this point is. So everything over here is going to be where my solutions are. So we're shading this side of the line. And again, it does not have to be perfect, but you want to get the point across. If you want to use the color pencils for this one, totally cool. It's not until we get to technically the next page that we really need to use both. Questions on this one? Okay, we're going to do it again, remembering, because the graphing of these inequalities is really, really important when we have inequality system. Super important. So on this one, are we doing a solid line or a dotted line? Solid line. We have an equals to underneath. That means it counts. We get to do an equals to. So we're going to do a regular solid line. Where's my first point going to be? 2. This is at my y-intercept. My b is this positive 2. So that's going to be this guy up here on our positive 2. How do I get my next point?
Can you choose the negative sign or
Just pick one. Yeah, because typically we do our slopes as up and to the right. But since we have that negative, I need to switch one of my arrows. So we could go down and to the right. That would switch this arrow. So if I go down 3, right 4. So down 1, 2, 3, right 1, 2, 3, 4. That's going to give me a point right here. And then I can do it again. Down 1, 2, 3, right 1, 2, 3, 4. Right there. I could also switch the other one. If I need more points, if I want more points, I could go, well, maybe I go up 1, 2, 3, and left 1, 2, 3, 4. That's totally valid. And then I picked up my pen and lost track of where it was. It was right there. 2, 3, 1, 2, 3. Yeah. And then up 1, 2, 3, up 1, 2, 3, 4. Right there. The more points we have, the easier it is to get our ruler lined up nicely. You just have 2 little points real close together. It's really hard to get that lined up right. So the more points you have, the easier it is to connect them up. This time we're connecting them with a regular line, not a dotted line. So traditional solid, we're used to drawing them lines. On this one, we also need to shade it. Whenever we have an inequality, we have to do the coloring part. We have to shade. So you can think about the fact that this is in slope-intercept form. Great, we love that. If it wasn't in slope-intercept form, we pick a point and we test it. You could always test a point, totally fine. We pick any point that's not on our line to see if that's going to make our inequality true. So since it's not on my line, I'm going to test 0, 0. And I want to know, if I substitute in 0, is this going to be true or not? So we want to know, is 0 less than or equal to negative 3/4 times 0, which is 0, plus 2. So is 0 less than or equal to 2? Yeah. 0 is less than 2. Totally fine. Which means that this is true. Which means this is where all my answers are. Which means I want to color this side of the graph. So we need to shade in this side. Again, does not have to be perfect. Just needs to get the point across. So before we look at the next bit on the page, I'm going to ask you guys a couple of questions about both of these graphs. I'm going to switch between them. So is this point in the solution? Does this count? Mm-hmm. Does this point count? Is this in the solution? No. Does this point right on the line, does this one count? Yes. Hush your face. Whiny computer. I'm going to do the same thing on this one. Looking at this guy. I'm going to make it not whiny. Is this point in our solution? Mm-hmm. What about this one down here? No. What about this one? Does this one count right on the line?
Yes.
On the first graph?
No.
No. If it's on a dotted line, it does not count as the solution. Because that's when we have our greater than. It has to be exclusively bigger than. It cannot equal. It could be really close. If I came just off the line just a bit, like right there, that's fine. If I was on 5.90, totally cool. 60, not cool. Doesn't work. Okay, so dotted lines themselves don't count for answers, but the solid ones do. If it's in the colored region, it counts for an answer. If it's not in the colored region, doesn't count. Because what we're going to look at now is we're going to look at how we had two equations of lines. We're going to look at two equations of inequalities. There is not a way for us to do these algebraically, so we only do these by graphing. So we're not going to have to substitute or do elimination with them. It's only going to be graphing with these inequalities. So we're going to start by looking at one they kind of half did for us. And all of the colors did not come out super great on your page. But this is a part of the reason we don't use the workbook, because they want to do 3/4 of the work for you. So if we look at example 1 right there, they've done the work for us and left us some very, very, super helpful boxes. And they're asking about, first things first, inequality 1. They've graphed it for us. This one, and I know it's very, very small up here. This top one, they call it inequality 1. Is this one did this one get a solid line or did this one get a dotted line? This top one. This one gets a solid line because, whoa, wrong pen. This one gets a solid line because it has an equals to. So on our picture that they've done for us, that's this line right here. This is inequality 1. And we used a solid line to graph that first boundary. And then they did the test point and they shaded it yellow, which does not print ever. So you could shade that with your colored pencil. That would be a good option for it, to use one color for this one. And for this graph here, it is not just the little yellow piece. This line, if I was to graph it all on its own, would have the shaded section. Ooh, helps if I draw right. This whole thing. This whole thing is the shaded region for that first piece. I don't know why I didn't pick yellow. I'm going to switch that to be yellow. And I at least match. So this whole thing is the shading for this line, all the way out. Then they graphed the other line. And on this one, since we don't have that equals to, they used a dotted line. They used a dotted line for it because it doesn't have that equals to. That's how we decide what kind of line we have. And then they shaded it blue. So I'm just going to color mine blue just so we can see what's going on here. When we are looking at systems of inequalities, our answers are going to happen in the place where it's true for both. So since we have blue and we have green, yellow, we're looking at this kind of blurbly green, gray. This. This will be where our true solution is. It has to be true for the yellow shading, and it has to be true for the blue shading. The line rules are also still in effect. Solid lines count, dotted lines don't. So what we're really doing with this picture is we're going to look at these lists of dots at the bottom, and we're going to see if it's in the true region. Does it count, or does it not count? The easy way to do this is by looking at the graph. You could also do them by substituting it into both equations. If it makes both equations true, then it works. If it does not make both equations true, then it does not work. But what we're going to do is we're just going to test these points, and we're just going to kind of hold them up to the light and see. So if we're looking at the point 1, -4. So 1, -4. 1, 2, 3, 4. This guy. Is this true for the yellow shading? Is this true for the blue shading? Yes. This one is true for both. It is in both the blue, yellow shaded area and the blue shaded area. So that one counts. This is a solution for this system. This one is. It is in fact 1, -4, 1, 2, 3, 4. It's, well, that point does not show up. There we go. It's the light green dot right there. That's where that 1, -4 is. I'm going to skip the second one for a second. I'll come back to it. I want us to look at the third one here for a second. 2, -1. 2, -1. So, 2, -1. Right on this dotted line. Is this true for the yellow shaded piece?
Yes.
Totally cool. Does this work for the blue shaded piece? No. It's right on the dotted line. If we were off the dotted line, totally cool. If we were this way. But not on a dotted line. I cannot equal a dotted line. So this one does not count. It is on the dotted line right there. Oop. So it's not a circle, it's a no. If you care, it's on dotted line. If it's on a dotted line, it cannot be an answer. Ever. It doesn't equal. So then, now we can look at the second one. I just feel like it's easier to look at the pure dotted line first. So if we look at 0.75u. Oh, there it is. -0.25. Oh, the intersection between the two lines. Will this intersection, where they cross, does this count? Why not? It's not true for both. We have a dotted line. So it's not true for both. So this one also does not count, even though it's where our two lines cross. It doesn't count because my blue line is a dotted line. Dotted line. So it's that point right there. I try and pick different colors just so y'all can, if you ever need to look back at it, see where things are talking about. And get another color with purple. All right, now let's look at a couple other ones that are a little less aggressive. We've got 0, -3. So 0, -3. This guy right here. What do you think about this one? I'm going to put it down on the screen. 0, -3. This light purple point right here. It's right on this line. Is it true for the yellow line? Yellow shade. Yes. Is it true for blue? Yes. If it's true for yellow and it's true for blue, good to go. Rock on. That one works. So this one counts. What about 4, 2? What do you think about that one? Because 4, 2 would be 1, 2, 3, 4. 1, 2. Way up there. I'm with you. Because that's a no. 1, 2, 3, 4, 1, 2. This guy up here is 4, 2. It's true for yellow. Blue's going the other way though. It is not true for blue. So this one is not true for blue. That is almost the same color. Not blue. You don't have to write like descriptions of it. I'm just trying to put things up there saying why, in case where they're not paying attention or have to look back at it later. Because things happen. Last one like this, and then we're going to go make our own. Dun, dun, dun. -3, 0. What do you think about that one? Nah. It's -3, 0. 1, 2, 3. It's over here. This guy. This one's true for blue, but it's not true for yellow. So this one is not a solution. It's not in the yellow. So it's not true for yellow on that one. So when we're looking for our answers, or if we have to name points that are true versus are not true, if it's on a dotted line, does not count. If it's on a solid line, totally cool. But it has to be true for both inequalities. Okay? So we are going to make one ourselves. Next page has 2 systems. I don't know that we're going to get through both, but we'll see how we go time-wise. We might just try one. So we are going to graph a system of inequalities here. So this is on page 17. We've got y is less than -3x plus 5, and y is greater than or equal to 2x minus 6. So this one has them both in slope-intercept form. We love that. This is when you're going to want to use your 2 colored pencils. I highly recommend picking a color to be each of them. I have a tendency to use like blue and red simply because then I can have purple be my intersection, but just because I'm extra like that. You can pick whatever colors you want. They don't even have to be vastly different. If you have green and blue, it's just going to be your kind of blurple over level. So I'm going to do this top equation in red, and I will do the bottom equation in blue. You can use whatever colors you want, but doing them in separate colors makes it a lot easier to tell where both of your shaded regions are. You don't have to. You can do it with the pencil, just like shading in lines or shading in circles, as long as it's visually different so you can tell where both is. So for my top one here, are we going to use a solid line or a dotted line? Dotted line. So I'll be graphing this one with a dotted line because we don't have that equals to. Where am I going to start? What's my first point going to be? 5. Positive 5 on my y-axis. So it's going to be up here. How do I find my next point? Down 3 over 1. And I'll go down 1, 2, 3 over 1. And then I can do it again. I can go down 1, 2, 3 over 1. Oop, wrong color. And go down 1, 2, 3 over 1. The more points you have, the easier it is to plot up your points, or to plot up your line. Remember to use a dotted line. Dotted, dash, I don't care how close together your dots are, but it needs to be a line using a ruler or a straight edge of some sort. I don't even care. Use something. Use a tool. To get our dotted line here. And then we need to shade. We can do a test point. If you know the shortcut way, that's totally fine. I'm going to do a test point because that's how we did it every single time on the last chapter. I'm going to test 0, 0. We have our 0 less than negative 3 times 0 plus 5. Well, we want to know if 0 is in fact less than 0 plus 5. Is 0 less than 0 plus 5? Yeah. So that's true, which means when we're looking at our graph, that is in my solution. This is true. That should be colored. So we're going to be coloring below the line. This side. And again, it doesn't have to be perfect. I'm going to get it probably better than I usually try to because we're going to be looking at the system. It doesn't have to be perfect though. What you don't want to do is to take your pencil and go super hard because then it's going to be really, really hard to graph the second line. So don't color it in super dark because you won't be able to see the numbers. Okay? It was like shading lightly, gentle. You color it in like this, you won't be able to see your numbers. We are going to do the same exact thing for the next line. Just with blue for me this time. So you'll use your other colored pencil, whatever your other color is. Creative choice. And we're going to plot up this next line. A lot of people still shade. Totally cool. Are we going to be using a solid line or a dotted line? Solid. Because we have the equals to this guy under here, we got to use a solid line. If we draw a line under the inequality, there's a line on my picture. Where is my first point going to be? It was there. It was a whisper. -6, yes. It's like I heard it. It was very quiet, but I heard it. It was there. So we're going to start at -6. How do I get my next point? Up 2 over 1. Up 2 over 1. Up 2 over 1. I can do that over and over and over and over and over. The more points you have, the easier it is to line up your ruler. Just because if I try and take my ruler, when I just have 2 little points, it's really hard to know if I should have it like this or like this or like this. With just 2 little points, it's really easy to be askew. So the more points we have, the easier it is to go, oh yeah, that's my line. I can only do that on my screen when I have the touch turned off. So we're going to connect it up. We're going to use a solid line. Getting it as good as we can. I am not super petty about, oh, well, you have it just slightly off. As long as it's hitting your points, we're usually okay. As long as it's not like way off. But the more points you have, the easier it is to connect them up. And again, I am going to do my test point here because that works no matter how it is that we solved this. We graphed our line, because the line we graphed is this equals to. So if it helps, you can write it like this. This is the line we graphed. But then we need to figure out where we shade. And I'm going to do that again by testing a point. I can use any point not on my line. My favorite bestie is not on my line, so I'm going to use it. 0, 0. We love her. She makes our life so easy because she makes things cancel out. But you can use absolutely any point. Does not have to be 0, 0. I just like 0, 0 is my favorite because she's easy to work with. We want to know if 0 is in fact greater than or equal to 2 times 0 minus 6. That's testing this guy. All that's saying is 0 greater than or equal to 0 minus 6? Is 0 greater than or equal to 0 minus 6? Yeah. 0 is in fact greater than negative 6. I would much rather have no money than owe somebody $6. I would much rather not have to give my non-money away. So since 0, 0 is true, that means everything on this side of the blue line is true. So when I'm shading, we're going to shade above this blue line. That's all the stuff up here. And this is where we can see it's nice to have two different colors because I can see the blue area, I can see the red area, and I can see my kind of blurple area. I'm going to come through and I'm just going to put a purple overlay over it so that we can actually see it a little bit clearer. This is the solution to my system, where it was colored true for both of them. Which is going to be a little dark up here, but that's okay. There is not a way to algebraically write out that. It's this weird kind of triangle-ish area. The only way we really have to convey this information is by drawing the picture or writing out the two inequalities. Sometimes we will be asked to pick a point that is in the solution and a point that is not in the solution. What is a point in the solution to this system? 0, 0. I mean, that's our test point. Sorry, my shoe went tight. I have to be down here. There we go. 0, 0. It's true for red. It's true for blue. Totally cool. What's another point in my system? Negative 1, 2. Absolutely. So is negative 4, negative 5. So is 1, 1. Barely, but it's there. What about this one? 1, negative 4. Is that in or out? In. What about this one? 0, 5. In or out? Out. It's on the dotted line. So points that are not in our system would be anything in the out here part. Anything out here is not in the solution to our system or anything on the red line. If it's on the blue line and inside the shaded region, that's when it counts. Okay? So our systems of inequalities are not super different than when we were working with lines. We just do two of them at the same time. So fast. Oh my gosh. I will pass out the last homework to you guys tomorrow. This is the last homework in the chapter. It's homework 6. It's going to also include what we do tomorrow and Monday, which is, I think, one of the grossest things we do in the course. So if you would like to have it to practice your inequalities, totally fine. I'll put it right here by the bin, but I know I've given you a lot this week, and so we are a little overwhelmed. I get it.